Well, I'm going to bring you back to the 16th century first. The Italians especially were interested in cubic polynomial, x cubed plus 5x plus 7, something of that sort. Now I'll draw you the graph of any of these cubic polynomials. Let us say I'll draw it qualitatively. Unless you're particularly perverse in your choice of cubic polynomial, it's going to look sort of like that.
This kind of distinctive wiggle.
There's a wiggle there. It looks like it's getting to a maximum, and then it changes its mind, and then it goes to a dip there, and then it thinks, oh gosh, this is a valley, and especially if the coefficient of the x cubed is positive, it'll go off to plus infinity, and otherwise it will be reversed. I'll draw you a few of them. Now you might say, why did I call this a few of them rather than just one? The reason is I haven't told you where the x-axis is. And I can change my cubic polynomial by adding a constant. So raising its graph by adding a constant, or lowering its graph by subtracting a constant. So maybe the x-axis of this one is there. The x-axis of this one is there. And the x-axis of this one is there. Now, once I have told you where the x-axis is, I can tell you when this polynomial is 0, at least graphically, because the zeros of this cubic polynomial will just be where its graph intersects the x-axis. So this one has only a single 0 there. This one has only a single 0 here. And this one has 3 of them. These would be the solutions of the equation. For example, this one, we would have to figure out which of these 3 it is, but it doesn't matter. We're looking for solutions to equations of this sort. So, as I say, unless you're really perverse, you either have 1 or 3 solutions. And it's in the 16th century that people began to get formulas, equations for the solutions of cubic polynomials. That is, say, for the solutions of when a cubic polynomial, of the problem when a cubic polynomial is 0. Now, something very funny happened. You'd think this guy has 3 solutions, so it must be easier to find them because there are 3 of them, rather than these 2, which have only 1. But it's quite the reverse. The equations that lead you to a solution for either of these 2 are, well, they're a bit of algebra, but a bit of algebra that's perfectly happily in the sort of mental theater of the 16th century people. This one was a weirdie. It was weird. And in order to solve this, these are real numbers. So all you have to do is work in real numbers. This one too. You work in real numbers and you get the solution. For this one, something very funny happens. I need another sheet of paper.
You can have as many.
This is the toughie. And now for this one, of course, the equation for this is real numbers. The solutions, there are 3 of them, are real. And in order to pass from the cubic equation to the solution, you have to do various things. And what seemed a little perturbing, and in fact, very perturbing to the 16th century people, was this passage. You'd have to pass through a region which seemed to be out of the, as I want to put it, out of the familiar mental theater of the mathematicians of the time, let us say imaginary numbers, or complex numbers, I'll say imaginary. The mathematicians were perturbed, but not that perturbed. And the first recorded instance of clear perturbation that I know is around 1545, Cardano, who had to use certain imaginary numbers. In fact, he had to use the numbers 5 plus the square root of minus 15, and 5 minus the square root of minus 15, in order to solve his equation, or to deal with this issue that he writes. Dismissing mental tortures and multiplying 5 plus the square root of minus 15 times 5 minus the square root of minus 15, you get, and he tells you how to do it, UL, the 5 times 5 is a 25. The square root of minus 15 times the 5 cancels the minus square root of minus 15 times the 5. The fourth term in these cross terms that you have to consider is the square root of minus 15 times minus the square root of minus 15, which, if you work it out, is 15. And so you get 25 plus 15 equals 40. And he writes, multiplying 5 plus the square root of minus 15 by 5 minus the square root of minus 15, we obtain 25 minus minus 15. And therefore, the product is 40. And thus far does arithmetical subtlety go, of which this, the extreme, is, as I have said, so subtle that it is useless. He's saying that he hasn't yet gotten into his mathematical repertoire this strange creature, the square root of minus 15, or complex numbers in general, and yet certainly has an intense understanding that we had better begin to deal with it, despite the fact that it may be subtle and useless. It's the first instance where someone complains bitterly and yet uses it, such a number. Yeah.
Does that still happen now, do you think? Or is it,
do we complain bitterly about things that we're on the verge of understanding but not quite? You know, I'm about to say yes. It doesn't matter what blobs they are, as long as they're similar. The counselor says, yes. What do you call that, says the king? Oh, I call that the blob Pythagorean theorem.